Okay, it starts recording now. So again, I think I'll leave you explain more the topic, Christian, and give you the floor. Thank you very much.
Yeah, thank you very much also for inviting me. So this time I decided to show some results of our work on the oxide dispersion strengthened, or ODS alloys. And this project has been a collaboration with our colleagues at Northwestern University in the United States. So in the lab of David Dunant, where my former PhD student, Christoph Kähnel, was a postdoc. And so we were swapping. I had his former postdoc, Anthony De Luca, now working with me. And we all worked on this project on the ODS alloys. So here's an outline of what I would like to present to you today. We'll give some background on ODS alloys, and then the work that we did, modification of a nickel, chrome, aluminium, titanium model alloy. This is a gamma prime strengthened nickel superalloy. Results from the fabrication of an ODS, of this ODS nickel alloy, using laser powder bed fusion. Then I will also show some results on the influence of heat treatments and give some results on the creep behavior of this alloy. And finally, a bit an outlook and also some information on what is currently going on here in our lab. Okay, so why ODS alloy, oxide dispersion strengthened alloys? This is a class of alloys that offers increased strength and in particular creep resistance in comparison to standard alloys. And this strengthening effect is obtained due to the incorporation of nanometer-sized, high temperature stable oxides in the matrix. And here you can see on this right-hand side what impact this has. So this is the specific strength, and this is the surface temperature of certain alloys. And you see all the structural alloys that are used, and in particular here, the nickel-based superalloys, which are used for the high temperature applications. And you can see that you can extend this field to significantly higher temperatures. And not only nickel superalloys are investigated. Besides that, ODS alloys are interesting for, the incorporation of nanometric oxides is interesting for steels, for cobalt alloys, tungsten, copper, aluminium alloys. So really a variety of alloys has been studied, with a few iron and nickel-based alloys having really found commercial applications. Just a quick reminder for why we get the strengthening effect. Well, this is textbook knowledge. You can really look this up in any undergrad textbook on material science. If we have particles in the matrix, well, then those are obstacles for moving dislocations. If the temperature is low, then we have the Aurovan mechanism, so that the dislocations, they really have to bow around the particles, leaving also these dislocation loops around the particles, which actually also act against incoming particles. At higher temperatures, the dislocations can climb, but in both cases, it requires additional energy really to drive the dislocations through the matrix. So we do have a strengthening effect, and the strengthening effect depends on the one hand on the particle size, which is here indicated in the equations by d, or the not the big D, but small d, and also the radius, and the volume fraction, or also the interspacing of the particles. So in short, we need many small particles, and so this is also a figure that you find in a textbook. The strengthening effect for these incoherent particles that we incorporate in the matrix is inversely related also to their radius or diameter. This means if they are very, very small, also the strengthening effect is much pronounced. And if we are really using high temperature stable materials for these reinforcement particles, so they will remain also stable at high temperatures. And then besides solid solution strengthening, the particle strengthening is the only strengthening effect that is efficient at high temperatures. So I mentioned that they have been around for many years now, and well, the conventional processing is a simple powder metallurgy approach. Means that you blend an alloy powder also with the nanometric oxides that you want to add. You mill those, that the oxide particles are also incorporated in the particles. You compact the powder, and then follows a thermomechanical treatment. So very often these compacted powders, it's actually filled in a can, it's rolled, it's forged, so you can really afterwards consolidate it. And well, this is actually finally done also by sintering. So it's really a solid state process. And as you can imagine, this sintering or powder metallurgy process does not allow the fabrication of parts with very complex shapes. And in addition to that, machining of odious alloys is very challenging. This is because we do have the strengthening effect. And if you start milling or turning, then also tool wear is very pronounced, and it's really difficult to fabricate parts with a more intricate shape from odious alloys. So with increasing use of additive manufacturing, many people then have also asked the question whether AM is a viable new processing route, because we see the high cooling rates, and that could then allow also fabricating odious alloys, really going through the melt and giving them also a very complex shape. Some words about that from our own research. Here I want to show you some results of a previous project that was running in my group. It was actually in the scope of a larger European project already several years ago. And that was the fabrication of an oxide dispersion strengthened gamma titanium aluminide. Here, just in short, also what we did, we did not only blend the oxides with the alloy powder, we did a complete mechanical alloying of the gamma titanium aluminide by high energy ball milling. And afterwards, we obtained the alloy powder. As you can see, we did not have very spherical shapes. Those are rather potatoes, but they worked quite well. And with this powder, we then started to do several tests. On the one hand, we did sintering, spark plasma sintering, which was a reference state. We used selective laser melting or laser powder bed fusion. And also we did direct metal deposition tests. And well, as you know, the difference between the two additive manufacturing methods is that here the cooling rates are significantly higher. The laser spots are smaller, whereas here this is closer to a welding process. Afterwards, well, we produced parts with different shapes, and from that we produced samples for further characterization. So here are some results of our work back then. We looked into, well, first of all, the presence of oxide particles, and yeah, they were there after all consolidation methods. So here we see the results from sintering, laser powder bed fusion, and direct metal deposition. As you can see, is that first of all, also here in the TEM images, and you see some spots here in the SEM images. So first of all, we could show that we had yttrium oxide, nano-sized yttrium oxides after the consolidation process in our material. And we could also show that we see a growth in the as processed condition with regard to the reference state. And this growth of the nanoparticles is correlated to the energy input. So the higher the energy input, the bigger the melt pools, the longer the melt pool lifetimes, and then also the bigger the particles that we finally find in our matrix. Still, we were very happy. We could also see that the particles interact with these locations. And we had a closer look into the performance of this alloy. We looked into the high temperature strength, where we could see an increase. We looked also into the strength at elevated temperatures. I did not mention it, but this was at 800 degrees Celsius, same as also the oxidation resistance of the alloy. So we could see an increase in all of that. Also, the oxidation resistance was significantly increased, which at that time we explained by the dissolution of some yttrium into the matrix and a stabilization of the oxide layer at the surface of this alloy. So that was very promising. And then we also were thinking about using this approach also for other alloys, such as nickel superalloys. And that was an interesting question. Now, coming to the nickel superalloys, so I'm sure many of you also know about that, but I still want to remind you of the most important properties. Well, these nickel superalloys, they are used for high strength applications because they offer very interesting properties really to high temperatures, and therefore they are used in aero engines and gas turbines. So the commonly used nickel superalloys, they do have a very complex chemistry. They contain up to 13 elements on purpose. I'm not talking about the impurities, but despite this very complex chemistry, their microstructure is fairly simple. So what we see is usually a gamma nickel matrix. Then in the high temperature alloy, we see the so-called gamma prime phase, which is an ordered nickel 3 aluminum phase, which makes this typical microstructure that many of you have seen in textbooks or presentations and anywhere else. And so then many of the elements are also added to form some carbides, which should lead to a further strengthening effect. So now if we think about also adding nanometric oxides, we want to increase, we're thinking about an increase of the creep resistance because we have also, let's say, we are combining the effect coming from the gamma prime hardening with the ODS strengthening effect. So if we have loads at medium temperatures, the contributions of gamma prime and the dispersoids are additive. And if we expose the alloy to very high temperatures, then the gamma prime might dissolve. But because we have added very temperature stable dispersoids, they should remain and lead also to an improved creep resistance at these very high temperatures. So that was basically what we had in mind. And then we were thinking about how we can do that. So I just mentioned, so let's first come to the modification of a powder, model alloy choice and powder fabrication. So I mentioned before that these nickel alloys, they can be terribly complex, and that also made us thinking whether we really want to look into a commercial alloy with possibly many interreactions between our dispersoids and other elements, or whether we really want to obtain some very fundamental understanding. We decided to go for the latter and designed an alloy that actually was a quaternary alloy consisting of nickel, chromium, aluminium, and titanium. And the composition was chosen to form rather high fraction of gamma prime phase, similar to commercial alloys such as CM247LC, but without any other phases to avoid these complex interactions with the added oxides. So here are some thermocalc simulations that you see where the gamma prime phase is stable. And we did some solidification simulations, equilibrium and Scheil. And well, we confirmed this later on the alloy. So we have a fairly narrow freezing range compared to other nickel-based superalloys. And we obtained powder from Nanoval in Germany, where we can see, so it's rather spherical. We do see some satellites here and there, but that was a powder that was good enough that we can work with it, and where we also had the required particle size distribution for laser powder bed fusion experiments. So that was just the base alloy. Now we had to make an ODS alloy from that. Because of our experience from the former project, we knew that we have to go for ball milling in order to really keep the oxide particles in our metallic powder. We had blends of 0.5 and 1 weight% yttria with a radius of about 10 nanometers. That was blended into our base alloy and ball milled. So afterwards, you see that we do have some deformation of the powder. Well, we expected that, but still the powder particles and the shapes there, they were okay. We knew that we can work also with morphologies like these. And the DSC measurements afterwards, they did not reveal any significant changes in solvus, solidus, or liquidus temperature of this ODS alloy. So here's also chemical analysis, and you can see that there is also some oxygen going into the matrix afterwards. Okay, so with these, we could start. And the first part of our work was really looking into the consolidation behavior of this ODS nickel alloy, and yeah, what effects the yttria particle have on the microstructure. So we also went for a very standard approach. So we varied the volumetric energy density. We printed matrix on our build plates where we changed so basically the laser power and the scanning velocity. I should mention we did that on our Simar Mycin 100. So what you can see here, this is the base alloy without any yttria, then 0.5% yttria, 1% yttria. And yeah, we did this parameter survey in order to find the best printing conditions. So what is obvious here, just looking at our cubes, at the surfaces of our cubes, is that the addition of yttria leads apparently to, well, a worse quality of our cubes. And in particular, we saw for this 1% yttria, this extensive pore formation, which is visible here. This is just stereo microscope, which is visible here at the surface. In particular, when the energy input decreases. So clearly indicating a deteriorated processability of our ODS alloys. So actually that was not the best sign, but we had a closer look into our materials. So this is low magnification SEM images, again, of our oxide-free 0.5, 1% yttria alloy. And yeah, what we can see is that with increasing amount of yttria, we do have really these large pores. And we explain that by a significantly changed wetting behavior of this yttria containing material. In addition to that, what we also see is the formation of slags, so larger areas or volumes where we have slags. We could see that in the base material, where we could identify these slags as aluminium, so Al2O3. The addition of yttria leads to the formation of this ternary oxidic compound, and the amount I will show that on the next slide, increased also with increasing amount of yttria. Well, basically we decided to discontinue the work on this 1% yttria because the results were not really promising, because we had these poor type of defects plus also extensive slag formation, and we decided to only continue with the 0.5% yttria alloy. So there, if we work also, well, if we change the processing parameters, so higher energy input actually led to a decrease of the slagging, but at the same time, we saw a significant increase of crack formation in our material. So for the 0.5% yttrium oxide alloys and the base alloys, we have quantified that a bit further, where we measured, of course, the density. So this is the absolute density, where we measured the crack densities, and where we also measured the slag area fractions. So where we just really measured the area of the slags relative also to the overall area. And so there are a couple of interesting findings. So first of all, the two alloys, they show basically similar consolidation behaviors. We could find a maximum density at volumetric energy density of 66 joule per cubic meters, so for these conditions. If we go for lower energy densities, then we saw lack of fusion defects, which is not surprising. So if we go for higher energy densities, then we see for both alloys increased crack densities, but this effect was much more pronounced for our ODS alloy. So the formation of slags, this is just the opposite. So if we increase the energy density, then for both alloys, the slag area fraction decreases, and this effect is also more pronounced for our ODS alloy. So this means whatever we do, it will be a trade-off between slagging and crack formation. Having a look at the grain structure of the two alloys. So here, this is the base alloy. These are some EBSD images that I'm showing now. The base alloy microstructure is characterized by elongated grains along the build direction, which is not surprising. Here we could not identify any pronounced texture in the material. We observe cracking, and this cracking occurs along the high angle grain boundaries, which is also very well known in nickel superalloys. What we see here is that they typically have smooth surfaces, indicating that we do not have solidification or liquation cracking. We rather believe that we have solid state fracture of weak grain boundaries, which is likely due to the high residual stresses within the part. That's not surprising because we just have a quaternary alloy without any grain boundary strengthening elements inside. Looking at our ODS material, we see these elongated grains along the build direction, but here we observe a very pronounced 100 texture. We also observe the cracks, and the cracking nature is the same as in the base material. So also along high angle grain boundaries, possibly also due to the lack of grain boundary strengthening elements. Now let's have a closer look into the microstructure. Anthony De Luca, my colleague, he did a very extensive TM analysis, and for that he prepared samples from our alloys perpendicular to the build direction, and he tried to find a spot ahead of a cracked tip so that we can learn the most from these TM investigations. So this is the base material. What we found interesting that in addition to these large aluminum oxide slag particles, we found alumina nanodispersoids through the alloy matrix which you see here. So even in the base material, we have kind of an odious alloy, not intentionally, but it seems to react with oxide, or they just seem to be there. We do have some sulfur as a contamination in our alloy, and we see scavenging of this sulfur by titanium, forming small titanium sulfide nanodispersoids, and they are co-precipitating with our alumina particles, as we can see in these element maps here on the right-hand side. These dispersoids are mostly found localized on the solidification cell boundaries, as we can see here, and they have radii of, well, slightly more than 10 nanometers. And we could not find any pronounced elemental segregation on the cracked boundaries, which also is indicative that we do not have any solidification cracking because of the formation of low melting phases along the grain boundaries. Having a closer look at our odious alloy, again, the sample was prepared in the very same way, ahead of a crack tip. What we see is a high number density of yttrium-rich dispersoids throughout the entire sample. What we also saw, so this is visible here, is a significant enrichment of yttrium along the grain boundaries. And elemental analysis suggests that we have this nickel 17 yttrium 2 phase. And we saw different types of dispersoids, basically, well, 4 types of dispersoids. So we found bright yttrium and nickel-rich dispersoids with a radius of around 16 nanometers. In addition to that, we found yttrium oxide-rich, but also yttrium oxygen sulfur-rich particles, which were significantly smaller. And we found some composite particles that were a bit more difficult also to identify. And these composite particles are an intermixed network of these yttrium nickel-rich and yttrium oxide-rich regions. And here, so also with some color coding, we've tried also to indicate the position of these oxides in our material. So this was about the processing. So let's have a first conclusion. So what we can basically say is, well, we can fabricate ODS nickel-based superalloys, but we do see different things. So the addition of yttrium oxide nanodispersoids to that gamma prime strengthened nickel superalloy leads to pronounced slag formation. So despite the short melt pool lifetimes, it seems that the overheating of the molten nickel alloy allows for the reaction of yttrium oxide with aluminium. And this forms a ternary compound with a reduced melting point. That might be mitigated by a reduction of the amount of yttrium oxide particles. We have seen that if we go from 1 weight percent to 0.5%, this had a significant effect. Possibly, but we did not try that, a reduction of the aluminium can also mitigate that effect, but with that we will also decrease the volume fraction of gamma prime that we have in our material. The ODS material also shows an increased crack density when compared to the non-ODS variant. So this is likely linked to the formation of eutectic nickel yttrium oxide along the grain boundary and possibly still some liquefaction cracking. However, these zones are very, very small. I said before that it's mainly really the solid state cracking, but it might be also that we do see some very, very, very fine regions where we still have the formation of liquid, but we would have to look into that. We did not do a very, very detailed characterization. And the formation of this nickel 17 yttrium 2 well, it's hypothesized that some of the yttrium-rich dispersoids that we find on grain boundaries dissolve during the layer-by-layer processing, followed by pipe diffusion along grain boundaries. So we do not think that they segregate during the solidification, but it's rather an effect coming from the layer-by-layer processing and also the multiple time reheating of the material, because we did not find these phases along the solidification cells, but only along the grain boundaries. We also saw that the ODS, addition of oxides, leads to pronounced texture formation. Apparently, our nanodispersoids, they lead to faster growth of the 100Zs. However, we do not have a, well, fully convincing explanation for this mechanism, and this is something that also we might have to look into in the future. But we see really very distinct differences between the non-ODS variant and our ODS variant. So, despite the presence of slags, we do see many yttrium-rich yttrium-203. So there is an S missing. So actually this is yttrium-2 oxide, oxygen-2 sulfur nanoparticles. They are dispersed in the matrix, and they are more usually found on the cell boundaries. And that is promising with regard to the potential strengthening effect. Some words about the slag formation. Well, we can reduce the amount of yttria, but if we look into the phase diagram between aluminium oxide and yttrium oxide, then we see what is happening. So they do react. So there is actually a eutectic point in this quasi-binary or in this vertical section. So there is a low melting region. And the question is, can we use other oxides, so not yttrium oxide? And so the typical thermally stable oxides of this type, M2O3, if we look into those, they all exhibit these eutectic reactions with aluminium oxide, which might result in slagging of the ternary compound. So that seems to be difficult. Then there are some other MO2 oxide dispersoids. They could potentially avoid slagging if they do not react with aluminium oxide to form a ternary compound. However, also in these ternary phase diagrams, eutectic points still exists, potentially facilitating the dissolution of these oxides. And again, so this is a bit a trade-off, and there is no ideal solution also to mitigate that. But it would be worth a try also to look into other oxides as strengthening material. Okay, so we continued our research and looked into the heat treatment response and finally also the creep properties of our alloy. So first of all, we checked the overall microstructure and the defect after the heat treatments. And so what we found is that after solutionizing at 1260 degrees Celsius for 2 hours, the crack densities for both the base and the ODS variants are reduced. So here again, we see crack density as a function of energy density. And so we see a reduction also here of the crack density. We also tried hipping at these particular conditions afterwards. And we could see that we can heal cracks also in both alloy variants. So we could actually make them crack-free, which also shows that, well, hipping is in that regard also an interesting way for post-consolidation. However, I do not want to follow that. So the following, I will only talk about the solutionized and then also aged samples. Looking into the grain structure, or also the defects, well, the cracks are healed by diffusion and sintering. So we see much less cracks, and what we also see is that the crack tips are very blunt in comparison to the S-process material. The porosity remains if we don't do hipping, of course. This is just a solutionizing heat treatment. We also see a pronounced grain coarsening after solutionizing for both the base and the ODS variant, with the grain sizes for both variants being similar after the solutionizing. However, what we observed, in particular in the ODS variant, is that we have areas, so fine grain regions, that are retained between large recrystallized grains in our ODS alloys. And we explained that here in these regions, we do see an effect coming from the nanodispersoates, namely that we do have some grain boundary pinning, which prevent these grains really from more excessive growth. Okay, so that was solutionized. We also did an aging treatment afterwards. The parameters that we use, they are very common for these gamma prime strengthened nickel superalloys. What we did is also very classical approach. So we measured first the hardness as a function of the aging time, both for the ODS alloy and our base material. Both alloys exhibit, so within the measurement area, a very similar hardness evolution. And what we observed is a plateau for the hardness for aging times at 850 degrees between 1 and 24 hours. Afterwards, we see an overaging effect. We then also went back to the microscope and had a closer look at the gamma prime grains that are forming during the aging treatment. And also we see here that while the aging behavior or the coarsening behavior of the gamma prime grains is very similar in both alloys. We then had a closer look at our dispersoids, and we saw that they are present, mainly located in the gamma channels. So here, what you see is, well, the bright phase in between, this is the gamma phase, and these darker regions, that's the gamma prime phase. So as I mentioned before, the volume fraction of gamma prime in that alloy is pretty high. And you can see that these dispersoids, they are really located in these channels. And having a look at the dispersoid size before and after the heat treatment, we can say that they show a very excellent coarsening resistance during the entire heat treatment. So we could measure on average an increase from about 8.3 to just 10.4 nanometers. So basically this is within the error between the S-printed and solutionized conditions. So this is a atom probe tomography result that we also did. So we were lucky. In one tip, we found both our dispersoids, and we could see also that they are really located in these gamma channels rather than in the gamma prime phase. So that was promising. Finally, we decided to do some creep tests. Well, because we did not have that much material, and we still were a bit concerned because of the cracks that we had in our samples. We decided to go for compressive creep tests at 800 degrees. And what we did is, well, we went for a stepwise increase of the load, the compressive load. Then this load is maintained constant until the specimen reaches a linear steady state secondary creep. And when that was reached, then we increased the load a bit and did the same. And with that, we could construct these creep curves. Yeah, what you see here is actually a comparison again between our base alloy and our ODS alloy. We tested the samples in both vertical and horizontal directions, so with regard to the building direction. And yeah, the ODS alloy, that was also interesting, shows, depending on the applied stress, creep rates which are 8 to 10 times lower compared to the base alloy, which indicates that we indeed see a strong effect of the added dispersoids. We see two distinct creep regimes. as identified by the power law creep exponent that we see here. So first we see a region where we have an exponent of 2, which is indicative for grain boundary slip. And then we have a region at higher stresses, which is indicated by an exponent of 5, which is indicative rather for dislocation glide. There is a certain creep rate anisotropy between the vertical and the horizontal test directions, and I think that can be explained by the elongated grains that we see, and also the pronounced textures. And so this is relative base material versus ODS. So there we see a pronounced effect. And so here, just for comparison, we compared it also with some literature data. So this is conventionally manufactured alloy, nickel 8 aluminium or Inconel 792. So I should emphasize that this is at higher temperatures also here. And it's just a model alloy, but the creep performance is good, and also it can be the effect of the addition of oxide dispersoids is also very pronounced. Having a look at the microstructure after creep deformation, so to a total accumulated strain of 3%. Well, the post-creep microstructure of the base and ODS alloy are very similar. We see the gamma primes within the grains with slight coarsening along the grain boundaries. We see cracks, and these cracks are confined to the grain boundaries in both alloys. So those are the weak spots, and also that is not surprising here. Still, we can see also some dispersoids here in our ODS variant along the grain boundaries. Also, making some conclusions for the heat treatment response and creep behavior. We see that we reduce the crack density of the ODS alloys, and also we see a recrystallization and grain growth. And both is beneficial for increasing the creep strength. We see that the dispersoids, they have an excellent coarsening resistance during solutionization and aging, means that they are temperature stable. And the introduction of yttrium oxide during laser powder bed fusion leads to significantly lower creep rates. So these dispersoids, they are assumed to interact predominantly with the dislocations moving in the gamma channels and increase the resistance of the disordered gamma matrix to deformation and creep. But in addition to that, the results also indicate that the dispersoids not only lead to dispersion strengthening of the matrix, but are also effective when located on or near the grain boundaries, enhancing resistance to slip. So some other ongoing work. So this was about our former work on titanium aluminide, which was oxide dispersion strengthened nickel alloys. So far, we have tested other alloys, also such as the solid solution strengthened alloys, Hastelloy X, Inconel 625. So that's pretty much straightforward, and that works. They show also a fairly good consolidation behavior. Together with colleagues at the Paul Scherrer Institute, we went for a 9% chrome steel. We could also show that we could consolidate those. We tried some aluminium alloys, in that case with alumina, and that turned out to be more challenging. That was laser powder bed fusion. We also work on direct metal deposition, where we made ODS titanium. And so one nice thing that we have is that in particular for direct metal deposition, we might not really have to pre-blend the powder or ball mill the powder. So also we have facilities that allow actually the simultaneous injection of both the metal powder and also the nanometric powder in one go by use of a specially so-called dense phase convey system, which we can actually mount also to our injection nozzle. And with that, we can also hopefully we have to try spatially vary the amount of nanoparticles. And the idea is also not only using oxidic reinforcement phases, but also other nano-sized ceramics. So with that, I want to come for the end. I thank you for your attention. So here, this work was funded really by the US Army Research Office. They do have also funds for funding international research. And yeah, the results, they are summarized in a couple of papers. Some of them are already out or will be submitted in the near future. Thank you for your attention, and I'm open for questions.
Thank you very much, and sorry for joining in late and having Roland introduce yourself. I had some issues with my connection. So I see we have a question from Manas. I think we need to be very short here considering the time already, but Manas, please.
Yeah, thank you very much, Christian. Very interesting talk. So in steels, usually when I want to look at oxides, I go to the Ellingham's diagram. That's the reference to know what kind of oxide would form in the material. But that's an equilibrium reference. So you look at what is the lowest Gibbs free energy and which oxide will result in the highest decrease. Now, that diagram does not have yttrium inside, and that is an equilibrium diagram. How would you explain the presence of both aluminum oxides and yttrium oxides based on a thermodynamic a chemical calculation like that? Like, because for me, in 316L, it should only be manganese oxides or silicon oxides because they're very close to each other. But in aluminum and yttrium, I don't understand why they should both be present.
Well, the answer might be that we do have this very, very rapid solidification, and we are far away also from equilibrium. So just not giving everything enough time to really also react, and that might lead also to the coexistence also of the two. We do see some reaction, but I think it is really this very, very short consolidation time.
Okay, we can discuss this more later. Yeah.
Interesting question indeed. Roland, short one?
Yes, I will be very quick. Just I'm just curious, do you think your yttrium oxides, do they melt in the process or not? Or are they just floating?
I do not think that they melt. I think they partially dissolve also in the matrix, but I don't think that they truly melt.
Okay.
Yeah.
So and the heterogeneous distribution, you say probably happened by diffusion, not so much by what happens in the melt pool, the circulation and the convection motions.
Not sure what you're referring to.
I mean, you said at some point that these particles then they dissolve and then they use the diffusion pipes to relocate.
Well, yeah. So probably we also have to discuss that afterwards. I mean, okay, they can dissolve. What we see is they can dissolve and reprecipitate. There are indeed particles that are pushed ahead of the solidification front. So what we see, this can be very complex and also very complicated to explain. Maybe I can also show you some more results from TM investigations, and we can discuss that separately.
Yes. Yeah. Thank you very much. Thanks.
Thank you very much.